Good morning, everybody. This is Apops 2 session. So before starting the session, I need to make an announcement. So I should have a list of the announcement here, but I don't. So let me seek information. So on Friday, we have a lightning talk session. So it's a small talk, like a 5-minute talk. So if you have something to share with this community, please submit your slides on the Apricot page. And also, tomorrow we have a social party, and it's a special opportunity to wear your national dress or Apricot and official T-shirts, right? And then, prize will be awarded to the best dressed. So please wear your national dress or Apricot and T-shirts given at the registration desk or from your stock. And then going to Apops content. So today we have 2 speakers for this Apops session. The first up is Beatty. Yeah. So you have a clicker here, and then you have 45 minutes.
For now. All right. Hi, everybody. So I'm Beatty Lane-Davis. I'm based here in Melbourne. I work for Cisco. I'm here to talk about subsea networking, which is a pretty interesting topic, but one that's, I'd say, fairly poorly understood. It's a very insular industry, part of the telecommunications ecosystem, I'd say, and there's really just not that many people that understand the design of subsea cables or the bits that go at the end to make them live. And the ones that do understand it don't speak English very well, not for language familiarity, just because they speak math and physics, 2 things I'm not very well versed at. So I wanted to give you guys, I guess, a bit of a history on subsea cables and just an overview of the technology that goes to what lives at the bottom of the ocean. Hey, man. And then I wanted to give an overview of the first generation of optical systems, and then talk about the coherent era and how coherent modulation changed subsea networking, and then talk about how coherent worked with the first generation of systems, and then talk about how that interaction led to a whole series of changes in the design of the actual cables themselves to optimize for performance. And then I want to talk about what's coming next, which is another interesting topic. So feel free to jump up with any questions or wait till the end. I'm easy either way. So, in a historical context, there's just nothing new here, right? We've been doing this since the 1850s. The first cable that came to Australia was laid in 1871. So we were doing this before we had phones, before we had antibiotics. It's bloody old. And we still pack a whole bunch of cable onto a ship and drop it off the ass end of the ship, and it gets carried across the ocean, and not much has changed there. And it doesn't actually happen a lot faster than it ever has before. So the big ship you see on the right there, that's one of these cable laying ships, which are really amazing feats of engineering in and of themselves. Those things have huge motors on them, huge engines on them to do all the stuff they need to do. And they also carry enough cable to get across the Atlantic in a single shot, which is pretty amazing when you consider that a kilometer of this cable weighs about 1.8 tons. So scale that out times Atlantic and boat size. It's pretty impressive. The picture down there in the middle is the actual hold where they spool up the cable literally by hand in a reel to play off the back of the ship. And down at the bottom is a shot of what these things looked like when they were conductive wires wrapped up in hemp and rubber in the 1850s, and what they look like now with the latest petrochemicals. It's not a lot's changed, which is interesting to me. This is a shot from the Telegraph Cable that linked up Australia off the east coast up to Canada in 1902. It's a big bunch of wire wrapped up in insulative stuff, so not a lot's changed, as I said. This next thing here is down at the bottom is this. It's a repeater that sat 19 kilometers off Bondi Beach from 1962 to 1984, helping get signal across that carried something like 80 voice channels for 24 years until they put this guy in. So this is a the electrical portion of a repeater that they dug up from, not dug up, but pulled up from 6 kilometers down, somewhere between Fiji and Hawaii, that carried on from the previous repeater you saw that brought something like 1,320 voice channels from 1984 until that guy got tired 20-something years later. So as I said, not a lot's changed. These cables are still, carrying something that carries a signal, which now is glass, fortunately, wrapped up with an electrical conductor, because this stuff requires power as it goes along, racked up with some sort of protection, all very carefully waterproofed, and then chucked off a boat. So there's a lot of nuance here. I mean, there's different types of cables depending on where you are in the ocean. If you're close to shore, there's a lot of anchoring, and they're big, beefy things, and down in deep water, they're, 2 centimeters across, this tiny little thing that just lives at the seabed for 25 years or more. They tend to be buried near shore or in places where there's going to be a lot of fishing activity. What cuts these things is typically what they call external aggression, fishing boats, anchors, that kind of thing. So you try to bury them near shore where there's likely to be a lot of activity, just to keep them out of trouble. And in recent years, there's been a lot of work around global positioning systems and ship transponders and actually services where a company will sit there and pay attention to where your cable is and then monitor for the ships that are going across it. And if a ship is slowing down where it shouldn't be, they get on the radio and say, dude, if you drop your anchor there, we're gonna hit you with a lofty bill. And that's actually brought the troubles down a long way, but people still find new ways of cutting these things. The bit in the middle is a remote vehicle that they send down to figure out where to trench and how to trench and all that kind of stuff. To give you an idea of what the trenches look like, this isn't to scale at all. The boat's actually a hell of a lot bigger than the trenching device, but you're talking about this plow at the bottom of the seabed that's getting dragged by this monster ship with 5 huge engines on it, going as fast as it possibly can, which isn't all that fast sometimes. And in Subsea, a lot of these answers become it depends, right? Especially how long is it going to take you to lay this thing is very much an it depends function. I heard a story of a guy who had to spend weeks and weeks going across the South China Sea because where they were trenching was just really hard. So the boat just sat there, full noise, going until they got through it, which interfered with some family plans, but how are you going to get off the boat, right? So the next sort of bit of critical infrastructure are the repeaters, these amplifiers that boost the signal periodically across the ocean, and they sit at the bottom of the ocean and generate photons for 25 years plus until they don't, and then you pull them up and replace them. But that doesn't happen very often because these things are designed for ultra high reliability, high availability. And they're also, as part of that, they're what's called gain saturating repeaters, which means they're just kind of turned up to 10 and chucked off the boat and left that way forever. So if you inject a single channel, the amplifier puts all of its power into making that as loud as it possibly can, which is really inaudible. But if you introduce a whole bunch of channels, you get kind of an even distribution of that amplifier power as you go. We'll talk more about that in a second. So that is kind of the biggest difference between the subsea amplifiers and the terrestrial amplifiers. Terrestrial amplifiers are kind of designed to be general purpose, so you can put them in any number of places in the network, and they can adapt to the span loss, the actual length to the next amplifier. They can kind of be variable, whereas subseas are designed specifically for that cable. So when you go to design a cable, you figure out how much you have to spend mostly, and then from that you reverse engineer what the spacing between the repeaters is. So the more you can pack in, the better the performance of the cable, but also the price tag goes up and to the right very, very quickly. And another big function of that is that, by having them on all the time without needing to have any sophisticated control loops between them and the next amplifier to figure out when they should be adjusting power levels, you keep it very simple. There's really no software living on these things. It's just an optical amplifier at the bottom of the seabed. And another big benefit of designing everything from scratch is that when you get an amplifier working at the exact gain range it wants to be at, it generates the lowest possible noise. So you put energy into these things, they generate light, they also generate some noise that you don't necessarily want. So by designing everything from scratch, you get a very, very quiet amplifier, I suppose you'd say. And the other big thing, I've mentioned this before, all of this comes down to dollars, right? So historically, the more you had to spend, the more repeaters you could pack in, and these things cost $1 million each, right? The more repeaters you can pack in to a given cable to keep the power level in the system high, but also the actual amount of transmission window that you can amplify is larger, the more you historically you'd spend, and that allowed you to get more channels in. That's changing a bit these days, but that's sort of the historical perspective. You also have what are called equalizers. So the amplifiers that we'll talk more about in a bit, they don't amplify uniformly across the transmission window because there's physics involved, right? So you put light in and stuff happens and it's not exactly what you want. So down here on the lower picture you see, without the equalizers, you kind of wind up with this big mountain looking thing, but you don't want a mountain, you want a plateau. And so you insert a filter that is the inverse of that effect to kind of give you that plateau shape you're looking for, and that's called compensating for tilt or ripple. And that works pretty well, but as you go along through a chain of these things, like if you're going across the Pacific and there's one every 70 kilometers, there's a hell of a lot of these amps, so that tilt builds up. So every so many amplifiers, I forget off the top of my head how many it is, but every so many amplifiers you'll insert a passive gain equalizer that's actually tuned on the ship as it's going along. So as they're laying out the cable, they can do loopback tests back to shore and figure out how much of tilt the amplifiers aren't compensating for, and then they can tune that on the fly, chuck it over the ship, and then keep that process going as they go across to give you the flattest spectrum you could get at the end of the system. There's also branching units, which are nothing more than branching units. It's kind of sorry.
You said questions at any time. I hope it's
Go
okay.
for it, yeah.
Previous slide.
Yeah.
This is Geoff Huston for the microphone,
Yeah.
by the way. Why wouldn't you do that when you build it in the factory, these equalizers? What changes as you throw it off the arse end of the ship that you're actually doing the insertion of these equalizers on the fly on the craft?
Things behave differently in cold water at the bottom of the
Oh,
seabed.
no, really?
Yeah,
So they just can't replicate that as they build?
I guess not. I know very little about this stuff. This is black magic. There's probably
Well,
100
it seems
people.
like black magic to me, and I'm just
Yeah.
sitting there going, holy crap, this is amazing.
Yeah, it really is, eh?
Okay.
And it's interesting. You can watch the system performance. You know, from looking at the modems, you can say, okay, I've got this bit error rate or this quality metric between the sides, and then as the temperature gets warmer over here and colder over here or somewhere in the middle, you can actually watch performance fluctuate.
Wow.
Yeah,
Thank you.
it's black magic, and we've been doing it forever, right? Scientists would say otherwise, but they're wrong. So these branching units are just topological routing devices. So they can be very simple in that, you know, if you have 4 fiber pairs going into the system from leaving Sydney, and I want to send one to New Zealand, I put a branching unit in, and that literally taps a fiber pair off that goes to New Zealand. Or they can be fancier, where they just take a bit of the spectrum and forward that off to New Zealand, but the whole fiber pair doesn't break out there. And more recently, they're software reconfigurable add-drop multiplexers that have gotten to the point in terms of system reliability where you can leave those sitting on the ocean floor and be able to reconfigure them from shore. But that's a pretty new update. But that, you know, the application there is for a cable like CME 3. Everywhere you see a white dot like that, this laser point. Oh, here it is. Yeah. So this is the trunk, right, that goes all the way wherever. And anytime you're breaking off on one of these branches, you have this branching unit that either sends off an entire fiber pair or sends off a quarter of the spectrum, or, you know, whatever it is, however you decide to break that up when you're allocating this. And these big systems just blow my mind, right? I mean, it goes from Germany to South Korea and Australia in a single run, so to speak. It's pretty astonishing. And to keep this all working, you got to inject power, because those repeaters need lots of power. So from either side, typically you inject, you know, for an ultra long haul system, you inject 15,000 volts of DC into this cable, and it runs through a copper conductor, and then the amplifiers are powered based on that, and it kind of runs all the way through. And you want to be able to have redundancy in the power system, so you've got 2 sides sending, or in the case of those, you know, massively diverse consortium cables like CME 3, you've probably got power at many of those points along the way. But in a simple point-to-point system, you're putting in power from both sides, so if one side dies, everything keeps working. And there's a lot of fanciness here that I really don't understand, but you can do cool things. There's this virtual C ground, right? But you can actually move that around by changing the differential between the 2 sides. And so if you wind up with a fault, an electrical fault on one side or the other, you can actually move the C ground to that spot to try to slow down the galvanic action there, because if you get a cut and it gets through the outer protective layers to the conductive layer, it just starts bubbling away at the bottom of the seabed, interacting with the seawater, causing heat and corrosion and all that kind of stuff. And eventually it gets to the point where it cuts the actual fibers, and then you're stuffed, right? So you realize by monitoring your power feed that something bad has happened in the middle, and you change the location of that sea ground to try to slow it down, and then you get a ship in the water, hopefully, as quickly as you can. Well, the ship's already in the water, but you get a ship sailing. There was a good example of that a couple of years ago when the Bastlink cable was being repaired, and the ship that was basically managing the South Pacific was off working on that, and there was another cable fault up towards Guam, and they couldn't get the ship there because the ship was in the Bass Strait. So eventually that guy got cut, and they had to bring another ship in. But those cuts actually look like this. So this is from the AJC, the Australia-Japan cable, and that's just a function of undersea currents and things rubbing the cable along the rocks, and eventually getting through that protective layer and getting to the copper, and the copper starts chewing away. And that was at, I don't know, 6,000 or 7,000 kilometers down. So when they go to do these repairs, you have a problem. You don't lay out enough slack with the cable to have 14 kilometers of cable to pull up at any one section. So when you want to repair this thing, you send a ship out. You know where they are based on GPS coordinates because you laid it there in the first place. And there's a whole International Cable Protection Committee that gets everybody to say where their cables are so that you know when you're crossing somebody else. And there's a whole series of protocols and all that kind of stuff. So you go to where the cable fault is, and when there's a problem, they inject tones on either side that kind of give the ship some idea from listening to a hydrophone where they need to be looking. They figure out where they want to repair it, and then they go and cut the cable. So they drop a big grappling hook off the side, it grabs the cable, they start pulling in that direction, and then eventually the cable gets taut and cuts. So that whole process takes about 20 hours, right? And you can only work to, say, maybe 6,000 meters of depth. So if you've got a fault deeper than you can work, and I think it's 6,000, if you've got a fault deeper than you can work, then you find the two sides that are shallow enough, and you cut there. Then you pull one side up, and you buoy that off, and then you go find the other side, you cut that off, well, you pull it up, I should say, and then water wouldn't have gotten in to, I don't know, the first couple of kilometers. So you cut the wet bit off, and you put in a really robust joint box and attach spare cable. And then you go steaming back to that other buoy that you just left bobbing there for a while. You pull that guy on, cut off the wet bit of that, join that guy together, and you drop it off the side again. So in a deep water repair, you're potentially putting in 15 or 16 kilometers of cable in between these two repeaters on a very tightly engineered system that may or may not like that. So you can actually see hits to performance that needed to be budgeted for ahead of time. So when you're putting the system in, you say, okay, it's going to work like this, but if you have this cut and this problem and maybe a repeater partially fails, there's redundancy built into all this stuff. If the repeater partially fails, then your system performance is going to go to here. So you need to be budgeting for the worst case scenario so that when bad stuff happens, everything gets working again once it all gets plugged back in. And I should have also said the repeaters are, the fact that they're always on and they're putting out as much power as they can provides a degree of self-healing. So if one repeater pump fails and the signal drops off a bit, it gets re-amplified as much as it can at the next repeater. So there's a degree of resiliency that comes from that. So like I said, these can be caused by tidal stuff, or you can wind up with like a typhoon in Taiwan a while ago caused a big subsea avalanche or earthquake, whatever you want to call it. Avalanche, yeah, that cut a whole bunch of cables. Or cars. So this is from a cable cut. I forget whether it was off Hong Kong or Singapore, but there'd been a big storm, and a Hyundai came off of shipping and it just fell and managed to find this 2-centimeter cable at the bottom of the seabed, and let's just say the Hyundai won. So they went to pull up the cable and they got a car instead. And I was discussing this with a guy who's been in this industry for a hell of a long time, and I mentioned the car thing. He's like, yeah, cars, anchors, shipping, fishing nets, bodies, that kind of thing, which is interesting. So if you're now considering where you need to stash a corpse, the ocean's probably not the safest spot, just for future reference. So to summarize, this stuff is, we're pretty good at it. We've been doing it for a hell of a long time, but it's very, very custom stuff. And at this point, I think there's about 3 companies in the world that actually do this at scale, right? There's Alcatel, there's TE Subcom, and there's NEC, because it's a massive, massive effort. You have to have ships that can go lay this stuff. You have to have ships that can go do the seabed exploration while you're figuring the routes out with very fancy sonar. You have to have the ability to manufacture this stuff. It's a massive project, and it's very consultative, right? So when somebody decides they want to get a cable in, they start engaging with vendors. The process goes from there. But at the end of the day, it all comes back to how much do you have to spend, and that's going to determine how powerful a system you can build. And these things are, it's hundreds of millions of dollars to get a trans-Pacific cable up, so it's a big deal. And the capacity is ultimately determined by the number of fiber pairs you have, how far apart the repeaters are spaced, how much bandwidth the repeaters can amplify across, the type of fiber, and as I said, how much money you got to spend. So let's talk about the first generation of optical systems. So the earliest optical cable was something called TAT-8 that went across the Atlantic, and that was it used fiber optics as opposed to coax, but it actually had active regenerative equipment sitting at the bottom of the seabed every 40 kilometers. So these things were, proportionally speaking, even more expensive to build. And if you wanted to upgrade the rate at which the line went, you had to lay a new cable, because you've effectively put a switch at the bottom of the seabed that you can't go back and reprogram. So, they started looking at plans for, a gig's worth of capacity when EDFAs started being developed. So erbium-doped fiber amplifiers, which are not a lot more than a loop of fancy fiber that has erbium atoms doped into it, melted into it. And folks figured out that if you pump in a lower wavelength of light into erbium-doped fiber, that light gets emitted, photons get emitted in the 15 nanometer range, which is what we care about. And that changed pretty much everything. So this is what a little EDFA looks like, or the laser portion of it. And it's not very exciting, is it? Lasers aren't very cool now that, they're cool, but they're not very exciting to look at now that it's all solid state as opposed to tubes with steam coming off them, that kind of thing. But yeah, that's it. So by having this capability of optically amplifying the signal rather than electrically regenerating it, you now have the ability to change the rates of the system by just touching what's on the ends rather than having to lay a new cable, which obviously gave these things substantially greater life and greater capacity, and allowing us to benefit from electrical advances rather than needing to lay more cables. So it's a different cost game entirely. And the first, there's a whole series of optical impairments that happen within glass. So glass is really good at carrying light, but it's not perfect, and it's kind of a pain in the ass in a number of ways. And the biggest impediment in the 10 gig days was something called chromatic dispersion, and that has to do with the speed at which light travels in glass. And so it doesn't, different wavelengths of light travel faster than others. So a channel on this side is going to arrive much, much later than one on this side. And even within a small bit of bandwidth that a channel's in, the signal gets spread in time, and you wind up with this jumbled mess up here in the upper right side where you can't figure out what's a 1 and what's a 0. And so there was a process to reverse that using dispersion compensation. So in the early days, that was all managed in the optical domain. So much like the EDFAs before, people found that if you let the dispersion build up for a while and then you put in a length of fiber that's doped with germanium dioxide, that's what it is, that reverses the process. So you kind of wind it up and then pull it back, wind it up and then pull it back, like Cameron, when they were trying to get the miles off of Cameron's dad's Ferrari in Ferris Bueller's Day Off by blocking it up on cinder blocks and putting it in reverse. That's very much the same process. So what you see down here is the blue end of the band. So when you model these things, you model one side of the transmission window, the other side of the transmission window, and then the guy in the middle. So the cable itself, through this compensation fiber, allows you to get the total amount of dispersion, be it positive or negative, to within the transmission, within the tolerances of the receiver at the far end. And that allowed 10 gig to work. The other thing, as I mentioned before, these subsea repeaters are just always on high. So in terrestrial systems, when you launch a single channel, the amplifiers work at this power to get it where it needs to go. And then when you launch another channel, they have to back down. And another channel they have to back down to try to keep the total power level at an optimal figure. And so that whole process involves a series of kind of control loops along the amplifier chain. And in subsea, you don't have any way of changing this stuff, mostly. So because they're always on high, we have to use what we call noise loading at both sides of the system to keep the total power level within that optimal range. And to do that, we use something called idlers, which is really nothing more than noise, like you get off an old stereo that wasn't very nice. If you turn it up loud, you just get a whole bunch of crackle. And so to create this noise, vendors take an amplifier and turn it up as loud as it could possibly go, and that puts out a bunch of crackle, and then they run that crackle through another amplifier, and that makes it even louder. And then you've got this random noise that you can inject into the total system. So as an example, if you've got a few channels of real traffic in the middle, you pad out the rest of the spectrum with noise to soak up the power, to stop those channels that you really care about from becoming too loud. So that's how we manage power in these, well, in all subsea systems, I should say. So in, 10 gigs started running out of steam. We needed something different, and enter the coherent era. So to start with, OnOff Keying, which is what we used previously, which is a matter of, flashing the light on for a 1 and off for a 0. It just couldn't really scale above the 10 gig mark, because if you can flash things on and off, and it becomes really hard to tell whether that's just gray or whether it's light or whether it's dark. Paul's got a better way of explaining this than I do, but he's sitting down, so that's fine. So when Nortel was busy imploding, they shut down a few campuses, and they consolidated the RF guys and the optical guys in the same room, and apparently over a lunchtime chat, the RF guys were like, what the hell are you doing? Why are you trying to solve it, in the physical domain? Why don't you just use DSPs to do all this? And bang, an entire industry was disrupted. So by combining really sophisticated digital signal processing techniques with the optical space, we found that chromatic dispersion didn't really matter anymore, because the DSP can compensate for that. And things like polarization mode dispersion that were really, really hard to deal with in the optical and the physical domain, with things like fiber doping and things like that, the DSPs could handle really easily. And so thanks to good old Moore's law, the chips were getting dense enough that you could keep up with optical line rates in a DSP. And so that kind of all came together in 2009, 2010, and all of a sudden you had this modem that could just go incredibly far. So coherent is phase modulation. So instead of using amplitude, light on, light off to send a signal, you actually modify the phase of the signal to embed information into a wave, right? So the squiggly thing here I pulled from Wikipedia. So if we embed the information in this blue stream to the carrier, which is this orange thing, we wind up with that lumpy looking thing down at the bottom. And then we can then run that through a decoder based off of this guy to wind up with this guy again on the receive side. And there's a little decoder ring that you see down on the left-hand side that says, if I start my squiggles here at the high point, that's a 1-1. If I start it here, it's a 0-0. If I start it in the middle, so on and so forth. And so effectively, you wind up modulating this stuff really, really, really fast in that sequence for a few nanoseconds, and then you move to the next phase, and the next phase, and the next phase. You send this complicated bit stream. And it provides a disconnect between the symbol rate, how quickly you're modulating stuff, and the bit rate of the signal you're trying to transfer. So 100 gig isn't really 100 gig modulated signal. It's 8 12.5 gig signals fudged together to give you 100 gigs worth of bandwidth. There's more to it than that, but not a lot. And so this thing down here at the bottom, oops, keep hitting the wrong button. This thing down here at the bottom you see with these 4 dots, you're going to see a lot of, is called QPSK, quadrature phase shift keying, and that gives you 2 bits per symbol, which means I can run at the data rate can be half the baud rate. The baud rate can be half the data rate. And if I send one of those squiggle patterns in a vertical polarization and then another one in a horizontal polarization, I'm now sending twice as much. So I'm sending 4 bits per signal, which gives me the baud rate of a quarter of the data rate. And this is all accomplished with something called a Mach-Zehnder interferometer. So this is a nested one over here, which is a pretty cool name, I reckon. And what you do is you send your bits in here, and you put them through a coupler. So with a coupler, it's almost like 2 bits of fiber melted together to a third one, right? So that sends half the light in one direction and half in the other. And you split it again, and then this guy up here at the top, this is the actual interferometer, where you send 1 bit of light around the fast path, and then the other one goes through that bottom path with a little rectangular thing on it. And by applying a voltage there, you can slow the rate at which it goes through. And when those two get combined again, the phase of the signal has been modulated. So if I do one of those for the the Y coordinates and one for the X. That's one of those square patterns. And then this other one down here gives another square pattern, and then the two are multiplexed to the vertical and horizontal and shipped on out. Pretty cool stuff. And there's a whole bunch of fancy math involved that I don't really understand. But this is all RF techniques, right? So, you launch the laser at wavelength 33, and on the receive side, and you run it through this, so it does the whole modulation thing. And then on the receive side, you turn it just off of 33, and you compare the incoming signal against what you know is 33, and you get an interference pattern that comes out. And then you run it backwards through this guy, and it gives you the bit stream on the receive side. And you can run fancier and fancier modulation schemes, right? So with the guy down here at the bottom, QPSK, that's just modulating phase, can give me those 4 points. But if I start modulating phase and amplitude, I can get these higher constellation points. So this is 4, this is 8, this is 16. And you can send that, but to get the fancier the signal is, the better the quality needs to be. So as an example here, BPSK is kind of the most primitive form of this. And if we use QPSK as a reference, BPSK signal can be minus 3 dB worse, or it can be twice as bad, and I can still receive it. And then I have QPSK, and then if I want to run AQUAM to get 300 gigs as opposed to 200 gigs, it needs to be 2.5 times better signal quality than QPSK. And if I want to run 16 QAM, it needs to be 5 times better. Meaning you just need a cleaner signal as you go along. So the other thing that makes this all, and again, these are all techniques that were borrowed from the wireless world. The other thing that makes this all happen is forward error correction. So you send that tight pattern of 4 dots, and then as it goes through the fiber, weird things happen to it, and you wind up with a pattern up here. And if you're looking at that middle guy, is he supposed to belong to the upper right or the bottom right? It's pretty hard to say. So we use FEC to let us figure that out, or let us correct some of those errors. So yeah, it's really just a matter of understanding that you're going to have a lossy environment, you're going to have a challenging environment, so you need a way for correcting that on the far side. So it just takes you take a bunch of information about the signal that you're sending, and you pad that out as overhead that typically lives in the OTN wrapper. So you're sending extra information. It's almost like RAID 5, right? You wind up with parity information that allows you to correct for errors on the far side. And that kind of reminds me of Mr. Sylvester McMonkey McBean, who had the machine that could put stars on things or take stars off. Because to me, it's a pretty similar function. And after I give this talk, inevitably somebody wants to come up to me and explain to me that FEC isn't as hard as I said it was. And then they start talking to me, and I say, please stop. It's hard for me, anyway. And they don't listen either, which is the funny part. So these FEC engines iterate, right? So FEC can tell you effectively what a value isn't. So if I say that one belongs to the upper right-hand corner, the math can say you're wrong. And so the FEC engine just iterates through. And so the magic in this stuff is the type of coding that you use, the actual math behind it, and then the number of gates that you can throw at that problem that give you the number of iterations you can run through until you get the right match. And this stuff only works to a certain error rate. And beyond that, it's useless. So if you wind up with loads and loads of errors, FEC can't solve it for you. But the first time I turned up a 100 gig network in New Zealand, we sat there watching these interface counters, and the list of errors was incredible. We thought, is it working? But the uncorrected error count that you wind up with is 0, because the FEC's just doing its magic. And like I said, the special sauce is really in the math and the amount of hardware you can throw at it. But we're really, with fancy modulation techniques and incredible transponders and forward error correction, we're getting pretty close to the theoretical limits, the Shannon-Hartley limit of signal quality in a noisy environment. And from here, we started with simple trellis coding, moved on to Reed-Solomon, moved on to turbo codes, and then everything gets really proprietary in a hurry when you're talking about long-haul stuff. So the actual implementation gains to be had from here are incredibly complex. It's really, really complicated stuff, and nobody really explained to me what the knobs are that they're turning. But the gains you get incrementally from here are very, very small compared to what we had a few years ago. So it's getting increasingly interesting. So that's coherent in a nutshell, right? So it uses RF technology, it uses phase modulation to run a really great distance with lots of capacity. And when that came out in 2000, I think realistically it was available in 2011 or something, they started running these over the existing 10 gig systems that had this dispersion compensation built in. And if you look at this graph, what this is telling us is that the middle part of the band, the middle part needs to be pretty much at 0 because you've got a tolerance on the negative side and a tolerance on the minus side, and you have to get everything in within there. So that green guy is pretty much living in an environment of 0 dispersion the whole way into the ocean. And so his signals get a little bit away from each other and they catch back up. A little bit away, catch back up, a little way, all the way through. And that's really bad for coherent. Because glass really isn't a static material. The light interacts with the glass itself. So when you pump a whole bunch of power into a fiber, the silicon dioxide kind of freaks out and jiggies around a bit. And you wind up with a whole series of nonlinear behaviors where, for example, I think it's simulated Brillouin scattering, the actual light decomposes into acoustic subparticles called phonons, and that causes the light to scatter all over the place. So you transmit something that looks like that, the 4 dot points that you see earlier, and then it starts getting skewed as it transits through the glass. So you just spent $50 gazillion developing this DSP to modulate the signal really, really nicely, and then the glass remodulates it for you in suboptimal ways, which is kind of funny. So this is a different view of it, right? So if you look up here at the right, this is after I think about 6,000 kilometers under the sea, and these are 10 gig waves. These all launched exactly the same way. And then as they went through the repeaters and they went through the glass, shaking around, they start looking different. And that guy in the middle, he's got these weird shoulders, and he's a bit fatter than when he went in. And that's something called self-phase modulation. So what the glass is actually doing when it shakes around and causes weird stuff to happen is interacting with the way the phase of the light travels through the glass. And phase is what you're modulating, right? So it's making life very, very hard. And here's a few examples down here of how this stuff skews around. There's something else I wanted to point out. So that, a big metric of quality in optical systems is something called the optical signal to noise ratio. And that's a way of figuring out just how much signal you're getting through versus noise. And if you look at this graph after transmission, right, this all probably went out, as a straight line. But this is the noise that gets accumulated along the way. And this is the signal poking out. This is just a whole bunch of pictures I pulled off, mostly off Wikipedia, a few other places. These are the BoseEinstein condensate graphs that you'd need to solve for to be able to do the quantum mechanical math to take all that nonlinear stuff out. And if you figure out how to do that, let's do a startup, but it's challenging. And these are some examples of launch power. So this, if I'm launching at, minus 1 dBm, meaning a little bit quiet, I get through with some reasonably tight dots, and I think these have to do with the number of amplifiers that you go through. But if I launch quite high, if I launch at 8 dB, you see how that signal starts to just get really, really skewed. And that skew kind of gives your forward error correction a lot to do because it gets very, very hard. This is an example of a 16 QAM constellation when transmitted, and this is on the receive side when it's all just kind of going. And so there's, some folks are working on being able to do nonlinear pre-compensation in their DSPs, where they actually skew things the wrong direction, and then the glass sort of brings them right. It's actually possible to do pre-dispersion as well. So a lot of digital DACs, digital analog converters, can predisperse in time, so that I could actually space the signals out as I'm transmitting them, so that as they travel through the glass, because you know what the characteristics of the glass are, it can wind up perfectly lined up at the far end. And it's interesting because you don't want to do that. That dispersion thing is really the problem, or the lack of dispersion is the problem. So when the symbols catch up to each other, they interact, they interfere with each other. And if they're spread apart, they don't. And so with these modern cables, you want more of that spread, because it gets them away from each other, because it's actually those interactions that are causing the problems. And for some reason, if you think about this in the time domain, if I'm launching at the same time and they spread out here, well, the guys that launched at T0 are away from each other, but this guy at T1 is lined up with this guy at T0. So why don't they interact? And the answer is they do, but not as much. And coming back to that, the ability to predisperse, this is all done by having these DSPs that can just do a zillion Fourier transforms a second, and you literally sort of sample your own signal as it's coming in and then play it back in time to wind up with how the signal should look. And so some vendors have the ability, as I said, to pre-disperse. And so there's an amount of dispersion compensation you want to do on the receive side because you want to get them away from each other, but there's an amount you can do on the transmit side as well. And so I sat looking at some graphs of just trials, figuring out if you do 100% on transmit, 0 on receive, and then a mix between the two, there's a sweet spot in there somewhere. And I looked at the guy showing me the graph and I said, why is that? And he goes, nobody knows. He used another word in the middle, but I think I'm being recorded. So coming back to sort of quality metrics here. So if I just go a little ways, I wind up with these nice clean bunches of dots that I can figure out. But after I go farther, it's a bit of a mess. And if that's a Q of 6, that's okay. Q is a quality metric. It's something you can relate to bit error rate. 6 is fine, because most transponders these days have a FEC limit of about 5.2. So if it gets a bit worse than this, I've got problems. But you think about the scenario we were talking about before with a deep water repair where something failed 7,000 meters down and you have to add 19 kilometers of cable or 16 or whatever the number is to fix it. I've engineered this system so that the repeater spacing is every 70 kilometers because I want to get a lot of capacity through, and then I make one of those 86. What does that do? So if I'm running it 0.8 dB margin, if I've got a FEC limit of 5.2 and I've got a Q of 6 here, and then I insert 16 kilometers somewhere in the Pacific, what does that do to that? So when you go to commission these things, there's sort of an agreement between the vendor and between the carrier. Your system is going to give us this performance. That's the carrier side, and the vendor side is yep. And I've got this much headroom for stuff ups, and all of it gets very contractual. Stuff ups, force majeure, whatever you want to call it. Yeah, so that's the nonlinear side of things. So realistically, on these older systems, because the guy in the middle just keeps interacting with himself over and over and over and over, his performance is going to be a lot worse. And so you wind up potentially in the situation where you can only run BPSK in the middle of the spectrum, but you can get away with QPSK on the bands because they're not as nonlinear. So the engineering of this stuff over the old systems was pretty colorful for quite a while. And the goal here is to get higher optical signal to noise ratio because that should give you a better quality performance. You should have a lower potential for bit errors if your signal to noise ratio is higher. But you can't just get that by launching more power in. Because as I said, here's the noise down here at the bottom and here's the signal. It looks like there's plenty there. But you can't just turn everything up to 15 and get good performance because things start to get weird. Those nonlinear effects are directly related to power and sort of power concentration within this very, very small bit of glass. So when you go to turn these things up, you do a test. You do a run of launch powers. You say, okay, well, here I'll try some more. Gets to this sweet spot here at about minus 1.5 dB, and that's when things are great. And then you try a little bit more, and it starts to roll off because things get more nonlinear, and your FEC doesn't handle it so well. So you back down and say, okay, well, this is where we need to be. And there's a real trade-off because you want to. Subsea carriers inherently are kind of torn between being incredibly conservative because these things need to work really, really well. So they need to be conservative on that side, but they also have this incredibly expensive sunk asset, literally sunk asset, that they need to squeeze the most out of. So that wasn't that funny. They're also trying to push as much as they can, and so you wind up with trying to get as many channels as you can with the best OSNR, but that winds up with these power problems. So the actual tuning of these things is it's pretty interesting. And like I talked about before, there's that tilt, right? So you build up an amount of tilt, and then you have that equalizer to correct for it. So this is a shot of kind of what the dynamics look like. That's either side of the transmission window as it's going through. I think that's 70 amplifiers or 70 repeaters at the bottom. So really, the PhDs like to act like this is real rocket science, but when I watch these guys turning this stuff up, a lot of it looks like a dude in a sound desk, just kind of adjusting the channels so they all kind of sound about right. And we talked before about the idlers, the noise loading to keep the power levels balanced. There's also something called constant wave idlers, where around that, the most nonlinear sections, you can just launch in an incredibly high power laser, a very narrow beam width laser, just to put a load of power into the system. So the repeater gets busy trying to amplify that, and that takes some of the power out of the more nonlinear zone, and that makes it more linear and less nonlinear. And again, there's some science to it, but there's also a lot of, okay, try it over here now, try it over here, see what you can fit over here, and maybe we can squeeze another channel in on either side. So it's pretty interesting to watch. So yeah, Coherent came out, and then new cables that were getting built since then were adapted to suit Coherent, right, which was about trying to make things more linear. And a lot of that was by just letting the DSPs do their thing, right? So getting rid of the compensation along the way. So instead of having some positive dispersion fiber followed by negative, you just have the whole thing as positive dispersion. In fact, the most dispersion that you can get. So the signals walk away from each other in time and interfere with each other as little as possible. And there was also a big push, because a lot of these nonlinear effects are just, they're a function of power density almost, right? So if you can just throw more glass at the problem and have a bigger effective area, the nonlinear effects are reduced. And that leads to some other interesting complications. And by the way, more glass is more expensive, so it adds to the cost of the system. And again, it comes back to how much you have to spend in the first place. So like modern D+ systems, you'll see, if you're going to a budget, you might have really large, like 150 micron area fiber coming out of the repeater, and that would go about halfway across the span, so maybe 40, 50 kilometers across, and then you'd switch to a smaller fiber so that you're only using, so you're only using the expensive spot halfway. And then once the power levels have dissipated, you can get away with the thinner stuff. And that's all part of this consultative, iterative process, right? And how do you get the splices clean enough, et cetera, et cetera? It's mind-boggling stuff. But if you take exactly the same transponder and you plug it into an old cable and then plug it into a new cable, bang, 10 times as much capacity, just like that. And the next step has really been gruntier DSPs. So legacy modems previously, legacy is what vendors call something that the other guys have that's a little bit older than the thing you have. So previously, if I had something that was, if I had a metric of 6 dB, right, the system was going to give me 6 dB or 6.5 dB, something like that. That's not quite enough to get 16 QAM. So I'd have to fall back to 8 QAM. But I've got way more margin than I need for 8 QAM. So I'm effectively leaving capacity underwater. And that's just due to the receive sensitivity here. So one approach to trying to optimize for that was to create hybrid modulation formats. So in the time domain, I would flash 16 QAM and then 8 QAM and then 16 QAM and then 8 QAM. And so I go from needing 5 times as clean a signal to 2.5 times. And the combined effect gives me somewhere in between the two bit rate wise, but needing only 3.5 times the signal performance. So it allows you to tune the modulation format on an incredibly granular basis to the performance of the system, so that you're getting the most performance you can have to the margin requirements that you're after. And that comes back to what the specifications of the cable are, plus the aging margins that you put in, plus accommodating for some of these repeaters to fail along the way, plus accommodating for a few deep water repairs and a couple of shallow water repairs over the 25-year lifespan of the system. And that's an interesting one, because like the web guys today, they're just throwing cables everywhere they possibly can. They're not running with margin. Traditionally the consortium carriers would say, I need a full decibel of margin, which is a lot, but if you want to have this stuff up all the time and accommodate for all this stuff over a 25-year lifespan, it's pretty conservative, it makes sense. But the web guys are like, stuff it, throw it in, because in 2 or 3 years' time, there's going to be a new transponder I'm going to put out there that's going to be better. So just forget the margin, right? And they probably have backup cables anyway, going some other direction. So I don't know, some of you radio nerds out there might be wondering why we're only talking about these sides constellation patterns, right? In radio, with I think 4G and 5G, you're looking at a big 256 QAM constellation, which is sending a lot more information per symbol than these guys are. But air doesn't get nonlinear. You can pump power out. It attenuates worse. It just doesn't get nonlinear. So glass, you kind of have to do with less, I suppose you'd say. So this is the grunty DSP argument, right? So you run the chip as fast as you can with the most forward error correction you can with the best combination of modulation format that you possibly can to tune the transponder to the wet plant. This is just another example, right? So this gives you 400 gigs, this gives you 300 gigs. If I need that sweet spot in the middle, I can get to 350 gigs. And this is all due to just incredibly grunty DSPs and smart silicon guys as well as physics guys. Yeah, and the next kind of trick coming down the street is something called probabilistic constellation shaping. where you flash this big monster 64 quantum constellation regardless of what the performance on the wet plan is, and then you tune the probability that you use the outer points, because those are the bits that are they're more likely to miss, right? So you tune the probability that you use those to the performance of the cable. And a different view of this is something like that, right? So you're more likely, there's a higher probability of sending these guys in the middle, but you flash the outer bits as much as you can because you're trying to drive your FEC engine as far as you can take it to get the most out of the wet plant that you possibly can. So that's kind of today, and coming next, the limiting factors these days are the capacity you can get per wave, and that's limited to the grunt in your DSP and the math behind your FEC and all of that. And then there's the available spectrum. So traditionally, all WDM transmission has happened in what's called the C-band, the ITU-defined C-band. There's also the L-band right next door to it that nobody's really bothered with. There's nothing wrong with it. Dispersion's actually higher than there, which is good for coherent. So there's been a push. There were I think one cable was built that actually used the L-band as well. And that's great because it doubles your amount of spectrum, but I should back up for a second. So the previous cables that we're talking about, I mean, the current speed record across the Atlantic is like 26 terabits. And you can loop that. We've looped that and gotten, I think, 19 terabits going back to Virginia across this cable. Across the Pacific, I think it was around 19 that we could get off a very high performance cable. And then if you use the L band as well, you could get another, maybe it was 18 and 14. So you can get to about 30 terabits across the Pacific using existing technology by using both bands anyway. But that winds up costing a lot more. And there's not as much equipment available, and it's hard work. And the other limiting factor is electrical power, believe it or not. That becomes the constraint on these like the Atlantic is pretty easy. It's what, 7,000 Ks, that's not so bad. But if you're trying to cross the Pacific all the way across without doing a regen in Hawaii, it's a hell of a long way. And so you run out of power. And so people are moving towards something called spatial division multiplexing. So the limit is getting the maximum amount of power you can to the bottle, but still getting all the way, the bottle's the repeater, but still getting all the way across the Pacific. So you've seen this graph before. Like when you go to tune the system, you push the power level to where you get the maximum signal to noise ratio, but what you're doing there is taking electrical power and turning that into optical noise, because kind of there's an amount of noise you can tolerate, right? And that's what your receiver likes, and then it gets too nonlinear, and that's too much for it. And people have been writing a lot of these nonlinear compensation algorithms to try to reverse engineer that quantum mechanics stuff, and it's not perfect. But one way I heard it explained was you've got self-phase modulation where you trip over yourself, and you've got cross-phase, and so you can actually go through and kind of figure out what was in the other phase of your own channel and try to subtract that from the first one. And I looked at the guy telling me this, and I'm like, but it's quantum. Like, how can, he's like, yeah, it kind of works though. And then you just let the FEC do the rest. So there are algorithms you can turn on, and what you can see is that, if you bring the launch power to here, and things start to roll off, if you turn these algorithms on, all of a sudden it bursts back up. And so you can actually use higher power settings with these algorithms, but fundamentally, your capacity is still limited by this Shannon-Hartley limit. And so instead of trying to optimize for maximum performance on a per channel basis, if you kind of step it back to maybe here, where you're saving more of that electrical energy, you can light up more amplifiers. I'm sorry, not more. You can light up more fiber pairs with a given amount of fiber pumps or amplifier pumps. And so instead of trying to get the maximum channel performance, you just say, well, stuff that. I'm trying to use my energy, my electrical energy more wisely. And so you spread the power out amongst using a bunch of these lasers, and then you spread it over a bunch of fibers themselves. And so you're running each fiber with worse performance, but you've got a bunch more of them. And this winds up giving optimal cost per bit. And so that's sort of where things are starting to head now. And nothing's in the water yet, but this is definitely the trend on where things are going. I had a few more points in the speaker's note, but they're not showing up, and my memory's not wonderful. So I think that's about it. Any questions?
Thank you very much. Any questions? Yes? You need to state your name and before questioning.
Geoff Huston, how far do you reckon it goes from here? At some point you've got a power problem, But if you put more cores in and reduce the power rate, you know, you're actually squeezing more efficiency out of that power, which seems to be the factor. And so the real question is, what is being designed today for laying in, say, 3 to 4 years' time? Where does it go?
Or another interesting question that I asked one of the guys who I used to work with is, what are we doing wrong with the cables we're putting in now that are going to interfere with what comes next after Coherent?
Right.
And the response to that was something. But where does it go? I mean, there's a chart. I watched a presentation recently, and I couldn't share the chart, but there's this function of the amount of capacity that you're trying to achieve and the distance, the amount of power you have to dissipate, and the number of fiber pairs. And there's this really interesting curve economically where you just wind up stacking more and more pairs. But like going back to this, I mean, this is really interesting because, you know, when I talked about the whole larger fiber, the larger effective area thing, more glass, that's counterintuitive to this because you're trying to pack a whole bunch of little guys into this tube, which changes the shape of the stuff that actually gets packed onto the ship. I'm not sure I have a good answer for you. I mean, for the time being, spatial division multiplexing is where it's at, and the capacity figures are through the roof. They're astonishing, and they're actually, there's other things they're looking at. Instead of using copper for the electrical conductor, using aluminum, of all things. Yeah, I know, that's what I said when I looked at it, but there's other tricks you can play if you use aluminum that you couldn't with copper. So a lot of it's a bit like high-end routers now, where like power and thermals dominates design. I mean, it's sort of the same thing where you're just trying to figure out how to work with the materials you have to change these things ever so slightly to get incremental boosts. But it's very interesting. I mean, right, like I said, we've all been working on these fancy modulation formats, probabilistic constellation shaping, and nonlinear algorithms to work at higher power levels. And in fact, like the cable that everybody's setting performance records on across the Atlantic was designed with higher power than was ideal at the time, because the assumption was that in X years' time, vendors will continue to improve those nonlinear tricks so that higher power is a benefit and not a liability. But that all kind of goes away here, because if you're dealing with a whole bunch of these little guys running with crappy performance, you're falling back to QPSK, whereas previously you could have done maybe 16 QAM across the Atlantic. Now you're happy with QPSK because you got a lot of them. And yeah, so where does it go from here? It's all still in research land.
I was actually going to look at your last point as well, lower dollars per bit, because doesn't the most recent cable set the price for the entire inventory? So if I'm a tenth of the current price in my next transatlantic cable, everyone else with inventory has a problem because they've got to match my price or run an idle cable. So what's the effective lifetime of the old cables when their target revenue keeps on declining?
Yes.
Yes. Okay.
Yes.
Good answer. Thank you.
No, that's 100% true. I mean, there's been a lot of some upgrades I was looking at doing. So, an upgrade being you just need more capacity on that fiber. Do you spend the money upgrading this older compensated system that's going to give you a 10% incremental, or do you spend this much more to wind up with an entirely new cable? It's interesting. Yes. Yeah, it's a fundamental problem, and it's inherently, like, if you look at some of the big consortiums locally who for the longest time had a monopoly coming out of Australia, anytime a new cable would be mentioned, they'd be like, hey, look guys, there's a sale. And that killed the other guy's business case, and that continued to happen for a long time. But now the inverse is kind of true, where these new guys can come out with astonishing price points. And the other thing that's really, I suppose, very interesting is what the web players are doing, right? Those guys are throwing cables in the water like nobody's business, and they're the ones consuming most of the bandwidth on the existing cables as well. So, I don't know. Yes. Good question.
Yep.
Thank you.
Okay, thank you very much.
Thanks.
So next up, and then Geoff, you have 30 minutes.
That's okay.
Thank you very much.
Now look, I'm quite happy to have seen it all the time, because quite frankly, the subsea cable stuff is amazing, truly amazing. This stuff is much more banal. I'm like, BGP, woo. My name's Geoff Huston, I'm with APNIC, this is BGP, woo. You all know about it, so nothing exciting here. I've done this talk a lot of times, and maybe most of you have seen this before, so a lot of this stuff is the same. But for those of you who have been lucky enough to have avoided my talk over the years, and you know, you're very lucky, but now, you know, you've got to endure it. There is some kind of preambles going on. And one of the preambles is that the routing system is actually quite unique in this world and in this internet. No one else and no other technology lets you see all of the internet at once from one point. Because the whole aim of routing is to bring all that reachability about all those destinations back to every single default-free router. So in some ways, this is the best lens we have at looking at everything all at once, because that's the job of BGP to actually do that. It's not perfect. Everyone has subtly different views, and we'll talk about some of them. But even so, this is one of the few ways where you see all of the internet all of the time. And interestingly, you actually see the economics and technology history of the internet by just looking at the routing table. You know, there's some technology artifacts. I'll use the left-hand side, lucky you. We thought the internet was going to die back in March of 1994 because, you know, the PCXTs couldn't take it, the valves collapsed or something. And so we invented classless interdomain routing, and that slight blip there is we saved the internet and all felt really good about it. This is the internet boom around 1998, 1999, where every man and his dog said the word internet, and all of a sudden billions of dollars of venture capital came your way. Euphoria existed, modems were wonderful, blah, blah, blah. That's the bust, where you actually get a lack of investment, things calm down. Interestingly, the telcos moved in across this period, and that rollout, which initially was DSL based, and then secondly, just around the middle of the decade, we saw the iPhones in the mobile market. And the slack on residential got taken up by this massive amount of stuff in your pocket. You'll notice in this sort of graph of BGP evolution that the catastrophe of egress exhaustion was basically bullshit. Not even a blip. Now, you could possibly say that was the global financial crisis, and you could possibly be right. That slight levelling off there was when investment capital left. But the technology blip of address exhaustion, meh. Crisis, what crisis? And ever since then, you could say running on empty, bullshit. You know, we've doubled in size and keep on going. So it's an interesting kind of history, and it's certainly not the way we thought it would happen. I said before that everyone sees the same internet. That's not exactly true. There's two large collectors of information out there. RouteView's archive, an NSF-funded program done by the University of Oregon, been going since 1999. Brilliant piece of work, fantastic resource. Route updates and route snaps every single hour from then till now. Secondly, project done by the RIPE NCC, similarly collectors all over the place. But isn't it odd when you look at each peer over time, since January 2017, and all I'm just doing is saying, how many routes are you giving me? Just count them. And oddly enough, there's more routes in RouteViews than there is in the RIPE-RIS. So interestingly, your view of the internet is subtly different to yours, because not everyone sees exactly the same network. Interestingly, it's not something that gets corrected. If you saw more routes than you'll do the same tomorrow and the day after. It doesn't waver very much. The folk with a lot of routes have a lot of routes continuously. The folk with fewer have fewer continuously. Interestingly, there's about a /8 of difference. About 17 million addresses are only partially visible. None of them are Googles, none of them are Akamai's, none of them are Facebook's, so no one gives a shit. Who cares? Phone isn't going to ring, don't care. Moving right on along, because all we are is a Facebook feed and network, aren't we? Moving right on along, sorry. The trends on the growth there, 51,000 prefixes per year, steady as a rock. Interestingly, autonomous system numbers, 3,400 per year. These aren't new service providers. I'm not even sure if it's new distinct bits of routing policy, but look at that line. It's linear. And if you actually analyse it a bit further, this is all Europe and North America. Not China, not Asia, not the Southern Hemisphere. So for you folk over in Europe and North America, what's this fascination with AS number, people? I'm like, why does every man and their dog and their mobile phone need their own AS number? They don't, but somehow they get them. In a linear fashion, 3,400 a year, steady as a rock for years. We always said that routing is a terrible way to do traffic engineering, and no one listened, because traffic engineering is done with routing. All the MPLS and other crap you like, no, traffic engineering is done by routing. So what that means is more specifics are slightly over half of the routing table and always will be. Has been for years, that's since January 2012, no change, nothing to see here, moving right on along. There's only one place where address exhaustion is obvious in the V4 network. Only one place. And that's the average size of a routing advertisement. Back in 2012, average size, 6,000/32s. Right, that was the average size. These days, yeah, getting close to 2,000. In fact, it's exceeded it. Sorry, getting close to 4,000. It's coming down lower. It'll hit 2,000. At some point, not that far in the future, we're going to have to look at ourselves and go, are we prepared to carry /25s? And I'm smiling, but it's a serious question, and the answer is yes. Because no one is deserting V4. No one. That is inexorable. It's not going to stop. And when it gets below 256, which it will, you're going to have to look each other in the eye and go, well, are we ready to quit V4? God, no. God, no. Too many people are using it. Right, /25s, here we come. Buy more memory. The other place where address exhaustion is obvious is just in the total span of addresses announced to the internet. Interestingly, that is not all the addresses that the RIRs have allocated. There's around 250 million addresses, actually a bit more, that we've handed out that we can't see. But nothing has flushed them out. At a price of $20 an address, it hasn't drained every cupboard. It hasn't looked in every nook and cranny. Oddly enough, the price is insufficient to bring more addresses into play. When we saw exhaustion back in 2011 back here, we pulled out another 10 or maybe 15 /8s, but that's it. $20 an address is not enough. If you want all the addresses out, think about $1,000 an address. If you want all of them out, $10,000 per single /32. That'll flush them out. But at the moment, the current price isn't doing that. So scarcity, interesting, not sure. The other thing that's going on is the way you interconnect. You don't find the closest point and jam yourself on at the end. Everyone wants to connect to the middle. So when we look at the inter-AS connectivity, the average path length, it's actually getting smaller. This is like a star collapsing to a neutron star. The diameter of the internet's getting smaller and smaller as we get bigger and bigger, because obviously, sorry, dropped my glasses. Obviously everyone wants to connect to the center, not to the edge. That's a good thing for routing, as we'll see. AS adjacencies, this is my view, your view is different. Every view is different from this, but oddly enough, it's heavily skewed. A small number of players have an extraordinary number of adjacencies, and everyone else just hangs at that one level out halo. So in the middle, from my view, 131072, I see 10 ASs with more than 1,000 adjacencies, and that's listed there. You might have one or two that are different, but this is basically the collection of folk in the middle, the tier ones of today's network. But the trail, oddly enough, for those in sort of maths land, log linear, says it's a power law. At that point, my maths ends, and someone who knows what a power law means and understands the implication of that power law, tell me the rest of the story, because I want to know too. That's been stable for years like that. That shape is exactly the same. So what can I say about routing in 2019? Meh. No one's made any changes all of you who have learned routing this year have learned from what you did in routing last year. So we've reached 800,000 entries, yay. We're doing 51,000 new entries a year, yay. We're doing 3,400 new ASs a year, same old stuff. And what about address exhaustion? Well, obviously Aaron's drained the pool. APNIC currently mid this year, but hard to predict. But in some ways, that sort of slope of APNIC is hitting the bottom down there. LACNIC's empty. APNIC, I've got a presentation on Thursday that studies that number in a lot more detail. Interestingly, it's up to you guys, right? How fast you drain the pool is up to you, and the range of answers is late this year all the way through to 2023 on the current stocks, which is around 2 million addresses. The RIPE NCC claims there's no free pool left. That's right, but there is a big reserved pool and an even bigger pool of unadvertised addresses. $20 a month isn't enough to flush it. The $20 per /32, 10,000 per /32, a lot more addresses are around. What's driving the growth? Well, why is the routing table growing when there are no more addresses? The last /8 policies in RIPE and APNIC grew it for a while, and the APNIC stuff is still going. Transfers is still driving a lot of this, and a certain amount of leasing and address recovery. I'm interested in understanding that. So let's look at the age of the addresses that appeared in 2010. So let's compare the routing table in January 2010 to the routing table in December. Lots of addresses disappeared, but a whole lot appeared. New addresses. And then I look in the records of all of the RIRs going, what was the date you handed that address out? How old is that address? So in 2010, 80% of all addresses were actually allocated or assigned in the last 12 months. So you went to the RIR, you got an address, you looked at it, had a cup of tea, went for a holiday, came back, put it in your router. 80% were in the last 12 months. 2% of all the addresses in 2010 were old as the hills. So all that legacy was untouched. So this is every year, exactly the same methodology right up until 2019. And you know, address exhaustion is obvious at this point, because here's the addresses that appeared in 2019 as a percentage. And what you actually see is that the recently allocated addresses, some RIRs redo the date. They make them new again. So this part of growth is all about transfer. But notice here, we're doing more and more mining of legacy. Around 20% of the addresses that appeared in the routing table are more than around 25 years old. So we are doing some dredging of the past and putting it out in BGP. And over the years, if you match those colours to that, what you actually find is a trend down to the left. And what that really is saying is, oddly enough, this middle of 5 to 25 years is where most of the addresses are coming from that are appearing in BGP each year more and more. So it's those kind of middle-aged addresses that actually have the most traction here in terms of mobility. So the total pool of allocated but not advertised addresses is still, this is from 2000 onwards, is still kicking around 50/8s. Should be 0. It's not. Folk who have addresses don't feel the need to sell them to folk who really, really want them. I read from this, and the fact that the number's going up, not down, is that folk who think that V4 is a scarce resource in this world don't understand the economics of scarcity. Because if it was scarce, you'd pay enough money to flush those out. But the price isn't enough. You don't feel that it's worth it. So there's exhaustion. That was actually the amount of assigned addresses. This is the advertised amount, but the unadvertised amount is going up. This is a look for 15 years of unadvertised addresses. There's one more. Oh, okay, yes, last year. So across the last 15 years, 30 up to 47/8s, grown by 50%. So more addresses are being stashed away than being used. Bizarre. So this is a harder graph to look at, but it's 2019 day by day. So let's have a look at some of these colours. The blue colour, look, I'll give a break for you guys, you can figure it out. Over here, the blue colour is the RIR allocation dates. So these are predominantly the last /8s and allocations out of APNIC. So RIPE and APNIC and APNIC, and some amount of transfers where Aaron changes the date. Thank you, Aaron. 5 RIRs, 5 different operational policies because, you know, they can. Bastards. Makes this so hard sometimes to understand this. The RIR allocations, and there were sort of busy days when they got really busy and gave out a lot of addresses. This is the growth in the advertised pool in the green. We handed out more addresses last year than appeared in the routing table. Now, they may have all appeared in the routing table, but at the same time things were disappearing out of the routing table. So this is net change. So this is the net change in advertised is actually only tiny, half a /8. The net change in the unadvertised pool, wow, 32 million addresses. Net were removed from the internet. Now, they may have been old ones, whatever, but 32 million got removed net for the year for all of the internet. Scarcity? If you guys were desperate, that red line would be negative, not positive. You're not desperate. You're quite happy with V4. Things are just fine according to these numbers. And if you go, no, Geoff, you're wrong, I don't see the evidence inside the numbers coming out of the registry, which is odd. So, you know, what we tell ourselves and how we act appear to be different right now. Fascinating. So that's the summary. You can read as well as I can. Go and look at the slides afterwards. I'm not going to waste time reading it out. Let's go to V6. Up and to the right, doesn't it feel like the 1990s again? The euphoria of V6, you know, whoa, boundless future. There was a slight amount of panic just around 2011 when there was exhaustion. But what I'm really trying to look here is, there were these V6 days when we're all going to run V6. Somewhere hidden in the noise is the V6 day. Impact, 0. The impetus of uptake is almost its own self-fulfilling state. That wobble is interesting too. Hopefully I've got slides on that. Yeah, there we go. Here's some of the wobble. Route views and RES. Fascinatingly, everyone sees the same internet now, plus or minus, you know, 10,000 routes. So less of this big banding going on. The default-free zone is roughly the same, apart from a few determined individualists who, you know. But everyone else roughly looking at the same kind of network. See that perturbation right at the end of the year, and I haven't actually analysed that in detail, but certainly a small amount of the wheels fell off. Things went flat for a while, and just around Christmas, it's sort of, wow, okay, back to work. Let's put in some more routes, doing a great job, getting paid by the route. V4, 31,000 routes a year, as I recall. V6, 17,000, half the pace. AS numbers, 3,100 in V4, 2,000 in V6. If this is a race, V6 is slower. The gap is actually getting higher, not larger, not smaller, on these numbers, which again, I find fascinating. More specifics, you've achieved the goal. You've actually reached parity. More specifics are now half of the routing table, yay. This is the one evidence that V6 is serious. You're now putting in as much pollution in 6 as you do in 4. Well done, everyone. This graph is odd. These numbers are so big, I've gone to a logarithmic scale, and I'm actually doing prefix size. So when I say the average size is getting smaller, that's true, which means the /n, the n's getting larger. So it's an inverse scale. Truly it is getting smaller, but not by a lot. Not by a lot. Average size right now, let me put on my glasses, it is indeed a /32. My guess is it's going to head to a 48 because half of the V6 table is a 48. And if you think, how big could the V6 table possibly get? Well, 2 to the 48. Ready? Got enough memory? Got enough computer? No way. Average address span, unlike V4, the average address span is growing and it's growing exponentially. It's now at the equivalent of 140,000 /32s is one way of looking at it. But the shape of the connection graph is almost the same as V4. Everyone wants to connect into the centre. From where I sit at my AS, the average length is around 4.7. Nothing much has changed. Who's big? Only 2 ASs have more than 1,000 adjacencies. So it's a smaller network in absolute terms, and that list of 5 is the top 5. And it's the same as V4 in some respects. Again, local to me, your numbers are different. The shape, I've compared the V4 shape to the V6 shape. It's the same power law, but there are just fewer players inside there. Interestingly, all the transit providers in the world are dual stack. It's the stubs that are so different. It's the stub networks that aren't doing V6. So V6 in 2000, and I said 18, I got that wrong, it really means 19. Whoops, sorry, silly me. 17,000 a year. Futures. You're going to buy a router. You want it to last 5 years. How big should it be? Well, interesting. This is the daily change for V4. 150 additional routes per day. It oscillates a lot. There's a lot of variation, but the average is around 150 additional routes per day pretty consistently. So I can do predictions based on that. And at the moment, 814,000, 5 years' time, a little over 1 million. Relatively linear. That projection is not a bad best fit, and indeed that one's pretty easy to track. It's going to be up to 1 million, and the rate we're going, they'll be down around 24s, and I suspect by the end of 5 years, you'll be routing /25s because, you know, pressure. V6, this is not linear, this is exponential. What you're seeing is the change rate, this is since 2012, is getting higher. That's that end of year anomaly. Some reason the number of new routes in the V6 network everyone called a halt for a little while. Bizarre. It's not clear what the long-term trend is. Not clear at all. There is a linear model, there is an exponential model. Both of them fit the curve reasonably. Now, considering that each routing entry is 128 bits long, if we are really talking 300,000 128-bit entries, that's 1.2 million V4 entries, yes? So in 5 years' time, whatever your fib might be, it needs to be a huge amount bigger if V6 is indeed an exponential growth rate, because this stuff is growing much faster than V4 if it's exponential. The data doesn't really tell you which. Could go either. So same amount of memory space in about 5 years' time. Is BGP scaling or failing? BGP is just fine. The average bandwidth consumed by updates is just fine. Let's have a look at the details behind that assertion. BGP is an oddly constrained system. This is the number of routes in the routing table. This is the V4 table. This is the number of withdrawals per day. There's 100,000 withdrawals per day, has been forever. You're allowed to withdraw today, you're not. You'll have to wait your turn tomorrow. You're allowed, and so on. There's this implicit sort of limitation on withdrawals. And you kind of go, what the hell is going on? As a system grows bigger, experience says, activity should grow. It's not. Withdrawals relatively constant. And the update rate isn't really the same either. That line there, the green and blue line, the updates per day, it was a bit of a bad year in 2019, but it didn't grow that much. More importantly, how fast is it? When a route starts flapping, It's going to reach a converged state eventually. How long does it take? In 2010 it took 50 seconds, in 2020 it took 50 seconds. What's wrong with BGP? Nothing. So updates in V4? Meh. As long as enough of you use MRI timers, and the folk who determinedly don't use MRI and BGP, boo, don't do that. MRI is your friend. And as long as the topology is compressed, then quite frankly, BGP works brilliantly and will continue to work brilliantly, because that combination of selective damping on updates through MRI timers and a compressed topology means this 30-year-old protocol, one of the few protocols that still exists after 30 years. I was talking yesterday, Reno was around 30 years ago, Reno is dead. RIP was around 30 years ago, RIP is dead. BGP, what else? IPv4, thank you, David. The Conservatives win, V4, IPv4 and BGP, okay. Put me off my track there, that was a good one. V6, this is slightly weird, and we don't know where it's heading, because, like I said, when V4, 100,000 withdrawals a day was bizarre, V6, that's what you'd expect. In both cases, the instability rate grows as the network grows. Now, these are much smaller numbers, but the number of withdrawals per day is increasing. Fascinatingly, from where I sit, V6 got a huge amount worse over 2019. You know, the update rate doubled inside that year, which is a bit disappointing. I suspect it's me. I suspect if I looked more broadly afield, no one else would have experienced quite that dramatic level of change. The good news is that convergence performance is getting better. While everyone was tunnelling V6, quite frankly, you only ran V6 if you hated your customers. That's gotten a lot better lately, thank Christ, because that kind of convergence performance, 150, 200 seconds, no one waits that long. That's just rubbish. It's now getting closer to 50, which is where V4 sits. And we know 50 is attainable because the rest of the network, the other protocol family, converges in 50 seconds. For some reason, as operators, you're not paying attention. You ignore V6. Why? Happy eyeballs means it really doesn't matter. The phone doesn't ring. Who gives a stuff? And the V6 network is much more unstable as a result. So the target is 50. Keep at it. That graph just explains what I'm seeing. Odd oscillation. Oscillation over a period of months. It goes unstable for some months and gets better for some months. Whoever is doing that, stop it. Okay, as far as I can see, BGP is under no great scaling pressure. The fib size is a problem, but quite frankly, the only way you're going to make more cost less is to actually start using smaller fibs in your line cards and actually go to hot and cold. There was a presentation done by Comcast about 4 years ago in Nanog that pointed out that about 94% of their traffic went through 380 odd routing entries. Most of your traffic goes to Google and Netflix and Akamai, right? Cloud for a few others, right? It's all a small number of CDNs. You're carrying 800,000 V4 routes, you're carrying 200,000 on V6 routes. Why? Why do they need to be in your high-speed line card? Well, the answer is they don't. And in some ways, we're going to see more and more of this sort of LRU cache in your line fib cards going, well, you've sent the packet to the wrong place. I'm going to drop that packet and load it up because you're going to resend and I'm going to have the cache hotted again by the time the next packet gets there. So my suspicion is if you're chasing a full fib, you're just paying lots of money for no benefit. You actually need to rethink the way you're provisioning your fib in your router cards and actually live with much smaller, cheaper fibs that work well for 95% of your traffic, and the other 5% will get there anyway, but that's the way you make money. So you should understand where you're actually loading up your fib, because as lines get bigger, the fib gets more expensive because the memory cycle time is now quicker and quicker and quicker. You're needing the absolute state-of-the-art memory to load up these fib cards. Understand where you're doing it. You should be using default as much as possible because default's cheap. Default's really fast. Explicit fibs are really expensive. Every single router these days actually lets you tune your V4 and V6 proportioning. You should visit that again and again and again because, quite frankly, the slot use is moving faster in 6 than 4. So you're going to have to retune that use. As I said before, use default everywhere because, you know, it's cheap. And like I said, hot caches. Why repeat myself? That's it. We're on time to the second. So there's room for one question. Thank you.
Thank you very much. Yes, go ahead.
David Woodgate, Telstra. I might have missed it when you were talking about the advertisements, but have you categorised the types of ASs that are increasing advertisements for IPv4, or releasing more v4 these days than previously?
You know, that's a really good question. And it's difficult to understand without a huge amount of work that I haven't done of the correlation between new AS numbers appearing in the net and IP addresses. We had this theory that, like, enterprise is dying, it's all in the cloud. And so we had this theory that the cloud itself was internally partitioning itself, and cloud clients, the folk who are renting space, actually came with their own AS. But although that's a theory, I haven't really looked hard at the numbers here. I don't think there's more edge enterprise with its own AS. No one puts computers in their basement anymore. It's so yesterday. So if the trend is I outsource into service land, which, you know, all the other sales rooms in this conference are talking about, then you kind of go, why are you using ASs? And therefore the question's actually a really interesting one. And unfortunately, I haven't done that analysis to give you an answer. But, you know, if any of the other APNIC worker bees are sort of listening to this transcript, get working. Thanks.
Thank you very much. Any other question? If not,
thank you.
Let's conclude this session. Thank you very much for attending this Apops 2. Once again, we have a right-wing talk session on Friday. So if we have something to share, slides is not necessary. So you need to submit your will or interest to share on the submission page. So thank you very much for coming, and let's going to break now.